So we're going to start moving away from derivatives and what derivatives mean and their applications and using those and start, which all of which is called differential calculus, where we're focusing on rates of change, how quickly things are changing, or graphically their slopes. And we're going to start talking about what's called integral calculus. And here, instead of how quickly things change, we want to know how much they change. In other words, we want to accumulate the change and find total change, not how fast it's changing. And graphically, in one of the later videos, you'll see that this is similar to area. It's not exactly the same, but it is similar to area. And I'm going to initially approach this from the idea of a train, because these are always classic math word problems. So we have a train moving at a steady rate of 75 miles per hour from 7 to 9 a.m., and we want to know what's the total distance traveled by the train. And for most people, they tend to think of it as distance equals rate times time. So distance would be the 75 miles per hour, and then the time we got by doing 9 minus 7 to get 2 hours. So we would have 150 miles for the distance. But what I want to do is say graphically what this is. So graphically, if we graphed the velocity, so our velocity was a constant 75 miles per hour, so horizontal line, and our time is from 7 to 9. Well, we can think of this as, if we notice that from 7 to 9, between our velocity and the t-axis, we have a rectangle. Well, our rectangle is 75 tall and 2 wide. And if you notice, the 2 we got by getting 9 minus 7. So here's the 2, and here's the 75. So there was the height, and here was the width, or rectangle, in which case we found the total distance by finding the area of this rectangle. And this is what I was saying before about their area is similar to what we want to do to find total change. There are going to be some differences that we talk about, but overall this tends to work pretty well for us, that if we can find the areas when we graph the rates of change, we can find the total amount of change. Now, where it gets a little more complicated, because of course we can't have nice constant volumes or velocities, is what if the train's velocity varies? It's not constant. And this is much more realistic in that we have trains speeding up on straightaways. They start slowing down when there are curves, or they need to stop when they get to a station and then start back up again. In which case, if we wanted to think of it in terms of area, we don't have a nice rectangle here anymore. So we have several options here. When you were in grade school and you had a complicated area to find, what you would usually do is break it into simpler pieces. That's pretty much what we want to do, but we don't have any control over our dependent variable, the velocity. All we can control is time. So when we break this up, we can only break it up in terms of the time. In which case I could say, well, instead of having one big chunk of 2 hours, let's break it up into 2 chunks of an hour each. But then I could break each of those up into 2 chunks of a half hour each. And I could break those up even more, and I could have 8 chunks of 15 minutes each. And if I notice, I can get smaller, and I get skinnier and skinnier shapes, but the shapes start approaching quadrilaterals that we know how to find the areas of, such as trapezoids or rectangles. They're not perfect, but if I keep making enough of these, and I think you can guess where I'm going with how many of these divisions I make, the curves at the top along the velocity graph get so small that thanks to linearization, we can think of them almost as lines. So the idea here is we want to break this up into simpler and simpler shapes towards an infinite number of those shapes that we can then treat as trapezoids or rectangles. And the idea of this is what's called a Riemann sum. So this is approximating the area under a curve found by breaking the region into simpler shapes, such as rectangles, trapezoids, or parabolas. And uh, we're actually going to talk about breaking them into all of those. But that'll start up with our next video.